A common ion occurs when you have either an acid or a base solution and a salt containing the same ion. So when we mix HF and NaF, we produce hydrogen ion, fluoride ion, and sodium ion. The common ion is fluorine. They're both producing fluorine ion. The common ion effect is the shift in equilibrium position that occurs because of the addition of an ion already involved in the equilibrium expression. So, for example, if we had HF and NaF, would the solution become more or less acidic than just plain HF, and why? So HF does not break apart 100%, while NaF does. So this is breaking up 100% into sodium and fluorine. When that breaks up, that means I start with some fluorine ions. When I have fluorine ions already in solution, then that's going to shift equilibrium to the left because my Q is going to increase. So to get my Q to equal my K again, then the reaction has to shift left, meaning there will be less HF breaking up. So H ions will decrease, making it less acidic. So let's see what that means mathematically. So the first part of this sentence we'll look at in a minute. So let's focus only on this part. So it says calculate the hydrogen ion and percent dissociation of HF in a solution containing HF and NaF. Whichever one you have the Ka for, that's the one that you're going to write your Rice table for, because the other one is going to dissociate 100%. We had 1 molarity of HF. And again, when this breaks apart, it's going to produce 1 molarity of sodium and 1 molarity of fluorine. We don't care about the sodium though, because that's not a common ion, but we do care about fluorine since that's in our equilibrium expression. And we don't have any hydrogen to begin with. Well, HF is going to go down some, and these will increase by some amount. We can write our equilibrium expression. So our Ka is equal to H times fluorine over HF. They gave us our Ka value. Our K value is rather small, so we can ignore our minus and plus x's. So multiplying by 1 divided by 1, x is equal to our concentration of H, which is equal to 7.2 times 10 to the negative fourth. To find our percent dissociation, we're going to do our x over the initial value, which was 1, times 100, of 0.072%. If we look back at the beginning of the problem, it said that if we had a pure 1 molar HF solution, its hydrogen ion concentration would be 2.7 times 10 to the negative 2. Notice our H concentration is much smaller in the one that has the common ion. And percent dissociation would be 2.7%. Notice again that the common ion is much smaller than the pure HF solution. So we're going to be talking about buffers in the beginning of this unit. A buffered solution resists changes in pH when either hydroxide ions or proton ions are added. So it doesn't matter if you add an acid or a base, it's going to resist changes. So blood is a buffered system. We have carbonic acid and hydrogen carbonate reacting in a buffered solution to keep our blood at a pH of around 7.4 pH. Small changes in your pH would cause your body systems to shut down. A buffered solution simply must contain a weak acid and a weak base. So you must have a weak acid and a weak base to have a buffered solution. A buffered solution results when the following are mixed. Number 1 and number 2 are the most common ways that we're going to have a buffered solution. We can have a weak acid and its salt, so HF and NaF, or weak base and its salt. We can get number 1 or number 2 by 3 and 4. So 3 and 4 are more how you would make 1 and 2. So 3 is you have a weak base and half the moles of a strong acid would be the best way of making a buffered solution. But really, any amount of the strong acid, as long as it's less than your weak base, would result in a buffer. I would have 0.5 moles of HCl. And then 1 liter of 1 molarity in H3, I would have 1 mole of NH3. When these get done reacting, I'm going to have some NH3 and I'm going to have its conjugate left over. And I won't have any of the strong acid anymore. That's how number 3 and 4 work. So I have to have a weak base and a strong acid, but I have to have less of that strong acid, so that way then I have the weak base and its conjugate left over. I can also have a weak acid and half the moles of a strong base, so like if I have NaOH and HF, when I'm done, I'm going to have HF and I would have NaF. So a weak acid and its conjugate, which is a weak base. So which of the following could be added to a solution of sodium acetate to produce a buffer? I'm going to pause the video and choose your answer. There may be more than one correct answer. So sodium acetate is a weak base. So acetic acid is a weak acid. So that would result in a buffer. Hydrochloric acid is a strong acid. So those may result in a buffer if I have less moles than the sodium acetate. So B is also an answer, but that isn't as good of an answer as A, because it doesn't tell me anything about amount. But again, if I had less moles of HCl than sodium acetate, then that would result in a buffer. Potassium acetate is a weak base. A weak base and a weak base do not make a buffer. And sodium chloride is neutral. Weak base and neutral do not make a buffer. So A and B are our answers, A being the best answer and then B being the second best answer. So let's see how we would solve these problems. Just like we did for the very first problem of this unit, we have acetic acid and we have sodium acetate. One of these they give us a Ka for. That's the one that we're writing the ice table for. It says that we have 0.5 of the acetic acid, we don't have any hydrogen, and then sodium acetate is producing 0.5 molarity of acetate because it's 0.5 sodium and 0.5 of the acetate. But that's the one I care about. Change, it's going down by some amount, up by some amount, and up by some amount. Your Ka expression. Plug in everything into that Ka expression. And then similarly to the other problem, we can ignore the plus and minus x. Our k is very small. And then multiplying and dividing by the same number means that our x is equal to our concentration of H. And it's equal to 1.8 times 10 to the negative fifth. So if I'm trying to find the pH, I can negative log my H concentration. Which is going to give me 4.74. In a buffered solution, the pH is governed by the ratio of acid to base. So HA means acid, and our A negative is our base. If we rearrange the Ka equation, we can get that our H plus is equal to our Ka of acid over base. The larger the acid concentration and base concentration are compared to the OH being added or hydrogen being added, the smaller the pH change will be. We'll see that later when we talk about buffer capacity. But we want large amounts of the acid and base. If we negative log our H, we get pH, and if we negative log Ka, we get pKa. Henderson-Hasselbalch equation is useful when calculating the pH of a buffered solution. Like we saw a second ago, pH is the negative log of H. So pKa is equal to the negative log of Ka. So we took this equation, we do negative log of H to pH, negative log of Ka is pKa, and then whenever we log the acid and base concentrations, they flip and we get base over acid. You can write it either way. Sometimes I'll use this bottom equation and just put B over A on there instead of writing out base over acid. So this is going to be useful when we have a buffer and we know the acid and base ratios. Or if we know what pH we want, we can calculate the ratio that we need. If we have more base than acid, then the pH will be greater than the pKa. If I have more acid than base, then my pH will be less than pKa. So let's see how we would use this equation. First, we say that we have lactic acid and sodium lactate. Those are a buffer because they both have lactate in them. We have a weak acid, and this is its conjugate, so it's a weak base. Since I have a buffer, I can go directly into pH equals pKa plus log of base over acid. I could also solve this like I solved the two previous problems in the video by setting up a Rice table, solving for x, and then negative logging it. But I can also just say my pKa is negative log 1.4 times 10 to the negative fourth. So that's my pKa plus log of my base. I need to know which one's my base concentration. 0.25 over my acid concentration. And then I just solve. So negative log of 1.4 times 10 to the negative fourth gives me that. And then notice I have more of the acid than base. So I would expect my pH to be less than 3.85. Solving it out, I get 3.37, which again is less than my pKa, so that makes sense. I have more acid than base, so my pH should be less than pKa. Go ahead and pause the video and try this one on your own. It doesn't matter if they give you an acid or a base, we're plugging it into our same equation. So in this problem, this one is my weak base. I know that because they gave me a Kb. And this is my salt, and that's my weak acid. Because they're conjugates, this one has more hydrogens, it must be the acid of the pair. I have a buffer then, because I have a weak base and its conjugate. So pH equals pKa plus log of base over acid. So I need a negative log my Ka. Ooh, but they gave me Kb. So remember that our Kw is equal to Ka times Kb. So I can find my Ka by putting Kw over Kb, and that's going to give me my Ka value. And so that's 5.56 times 10 to the negative 10th. So I can negative log my Ka plus log of base, my base is 0.25, over my acid 0.40. My pKa is 9.25. And if we look at it, I again have more acid than base, and so I would expect my pH to be less than my pKa. Solving that out, I get 9.05, which again is less than my pKa, which again makes sense since I had more acid than base. Alright, go ahead and try this last one on your own. To simplify the question, I've already given you the pKa. Restart when you have your answer. So on this one, we first look and see, do we have a buffer? This one is a weak acid. This one is its conjugate, or a weak base, so yes, I have a buffer. So pH is equal to my pKa, which was given, plus log of base concentration. They gave me moles though, so I have to divide by volume, but in this case it's just 1 liter, so divided by 1 is still 0.5 over my acid, so 0.3 divided by 1 is 0.3. Notice in this case, I have more base than acid, so I would expect my pH to be greater than 9.4. So plugging that in, I get my pH is 9.62. But this problem was a little tricky because it said, what is the POH? Well, once I know my pH, then I can find my POH by saying 14 minus pH, or 4.38.